This is 10.5, the binomial theorem. What we're going to talk about today is working with two-term polynomials and raising them to exponents. We need to start by remembering some things we know about exponents. I know that anything raised to the 0 power is 1, which means that when I raise a plus b to the 0, I get 1. I know that anything raised to the first power is itself. So when I raise a plus b to the first power, I get a resulting polynomial of a plus b. We can keep going. We have some rules that govern certain binomial multiplication. When I raise it to the second power, I should get a squared plus 2ab plus b squared. And when I raise it to the third power, I should get a cubed plus 3a squared b plus 3ab squared plus b cubed. I want you guys to pause the video and expand to find a plus b to the fourth and a plus b to the fifth. You can do that either by squaring a plus b squared or by multiplying the result of a plus b to the third times a plus b. Alright, let's check our work. For a plus b to the fourth, I ended up with a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. And for a plus b to the fifth, I ended up with a to the fifth plus 5a to the fourth b plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the fourth plus b to the fifth. We're going to talk about these patterns that we notice down below more formally, but while we're looking at these specific problems, I just want to point them out as we go. So the first few things I notice that the lead term, a to the fourth, our lead term, a to the fourth, is our first term raised to the exponent. I also notice that my last term is b to the fourth here and here. Same thing happens down below, right? B to the fifth ends up as my last term, and a to the fifth is my first term. From there, I notice that my a values descend, right? 3, 2, 1, or down below 4, 3, 2, 1. And then I also notice that my b values ascend, right? I have no b value, then I have 1, 2, 3, 4. Down here below, I have b to the first, second, third, fourth, and fifth. I hopefully notice that when I have a fourth degree binomial expansion, I end up with 1, 2, 3, 4, 5 terms. And down below here, when I have a fifth degree binomial expansion, I have 1, 2, 3, 4, 5, 6 terms. So I always have one more term than the exponent. And finally, the last thing I want to notice here is that the exponents should always add up to the original exponent on the binomial expansion. So here, I'm raised to the fourth power. This is a 4. This is 3 plus 1, which is 4, 2 plus 2, and 1 plus 3. Down below, I wanted to get to 5, so I have 5, 4 and 1, 3 and 2, 2 and 3, 1 and 4, and 5. So let's formalize those patterns that we notice with binomial expansion. I'll type these out so we can see it clearly. Alright, here are the formalized patterns that we should notice on binomial expansion. The first term is a to the n, and the exponents on a decrease on each successive term. The exponents on b increase by 1 on each successive term, starting with 0 on the first term. The last term is b to the n. The sum of the exponents on any term is equal to n. And finally, the number of terms in the expansion is 1 greater than n, so a plus b to the n has n plus 1 terms. Something that I think we've seen before is Pascal's triangle. It is a structure that contains patterns and shows up in various branches of mathematics. The way we create Pascal's triangle is we start with a triangle of 3 ones, and we create each successive row by putting a 1 on the edge on the first and last term, and add up middle terms to create add up the terms above to create the middle terms. So what do I mean by that? If I look here, I see that I start with my triangle of ones, right? 1, 1, 1. And then this 2 comes from the sum of 1 and 1 right above it. So the next row will look like 1, 3, 3, 1. The row beyond that will be 1, 4, 6, 4, 1. The next row will be 1, 5, 10, 10, 5, 1. And for now, the last row we'll look at will be 1, 6, 15, 20, 15, 6, and 1. What I'm hoping you notice is that these rows here, let's see, we should recognize this row, we should recognize this row, and we should recognize this row. These are the coefficients for our expansion back at the beginning of our lesson, right? 1, so let's see. Here we have coefficients of 1, oh, sorry about that, 1, 2, 1. Here we have 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. All these numbers match what we see in Pascal's triangle. So we'll circle back to this and another use of Pascal's triangle when dealing with binomial expansions. For now, let's just turn over to the next page and talk about something called the binomial coefficient. So the binomial coefficient, the way we write it like so. It's going to be in parentheses n over r. And that's just how we would describe that. We would read that as n above r. N above r. And the formula associated with n above r is n above r equals n factorial divided by r factorial times n minus r factorial. Now hopefully you recognize this. This is very similar to what we saw in our combinations unit. This is actually the same formula we use when creating combinations. So we can evaluate a few of these. I'll walk through one of them, and then I'd like you to try the next two on your own. So when I have 6 above 2, I can write this as 6 factorial divided by 2 factorial times 4 factorial. And the way I see this in my head, I know this is going to be 6 times 5, and then times 4 factorial over, well, I know 2 factorial is 2 times 4 factorial. Those will cancel. So really, I'm going to end up with 30 divided by 2, which is 15. At this point, I'd like you to pause and try to evaluate each of the following binomial coefficients, 5 above 2 and 5 above 0. All right, let's check our work. So for example B, I ended up with 5 factorial over 2 factorial times 3 factorial. Once simplified, I ended up with 10. On part C, I ended up with 5 factorial divided by 0 factorial times 5 factorial. Remember, 0 factorial is the same as 1. So we ended up with 5 factorial divided by 5 factorial. And then on part D, we ended up with, we started with 9 factorial divided by 3 factorial times 6 factorial. Once we simplified and evaluated, we ended up with, I ended up with 84. We can use this binomial coefficient to more quickly and efficiently simplify a binomial expansion. So the binomial theorem tells us that we can write a plus b to the n in the following way. We can write this as n above 0 times a to the n plus n above 1 times a to the n minus 1b plus n above 2 a to the n minus 2b to the second. And let's just get ourselves some more space here. And we can see the pattern. We'll cut it off there. We'll go plus dot 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 plus n above n times b to the n. So altogether, we end up with a string of numbers that we're adding together. So that means we can write that in sigma notation. Now, we're going to use as our index our r value. So we're going to start r at 0. This 0 here matches with this 0 there. Okay? And then we're going to use our sigma. You know what, let's get this all uniform. Let's put that in black. In our last term, we go up to n, which should make sense. If we have n terms and we also include 0, that means we're going to have one more than n terms, which matches what we saw on the first page. Now the form we see here, we have our binomial coefficient here, n above r, times a to the n minus r times b to the r. So for binomial expansion, we can use this summation here. Let's look at one example together, and then you're going to try one on your own. So if I want to expand x plus 2 to the 4th, my a value here is x, my b value here is 2, and my n value is 4. So if I want to expand this, I can write this as follows. I can write this as 4 above 0 times x to the 4th plus 4 above 1 times x cubed times 2 to the 1st plus 4 above 2 x squared. I need some more room. Squared I'll get x cubed to, oh, sorry about that. I should have x to the 1st, 2 cubed, plus 4 above 4, 2 to the 4th. So now all we need to do is evaluate each of these. I'm going to go the long way just so you see what's going on here and evaluate each of these individually, and then we'll get our simplified final answer. So this first term here, let's put in a different color so we can see it. This is 4 factorial over 0 factorial times 4 factorial times x to the 4th. And as a result there, we should get x to the 4th times 1, which is x to the 4th. We're going to add to that 4 factorial divided by 1 factorial times 3 factorial times x squared times 2. Well, 4 factorial divided by 3 factorial is just 4. 4 times 2 is 8, so I should add to this 8x cubed. Our third term, we will end up with we're going to add to this 4 factorial over 2 factorial times 2 factorial times x squared times 4. So what I end up with here is 4 factorial is 24. 24 divided by 4 times 4, I end up back with 24. So my simplified form of this term is 24x squared. Let's keep moving here. We have 2 terms left. So to this I'm going to add 4 factorial over 3 factorial times 1 factorial times x times 8. So really, this is 3 factorial being, 4 factorial divided by 3 factorial, which gets me 4. 4 times 8 is 32. So I have 32x. And then remember from above, when I had 4 above 4, it's the same as if I had 4 above 0. I'm going to get 1 as a result. So I really just have 2 to the 4th, which is 16. Let's zoom out. So my final answer here should be x to the 4th times 8x, plus 8x to the 3rd plus 24x squared plus 32x plus 16. So I'd like to let's look at example 2. I will show you guys the setup and then let you work through it and show you the final answer that I got. So the setup should look like this. The setup will look 5 above 0, 2x to the 5th. And whenever you have a coefficient on one of your terms in your binomial, make sure you're using parentheses. It's going to make things much less complicated. I have 5 above 1, 2x to the 4th, negative y plus, I'm going to zoom in so I don't run out of space quite so quickly. We should have 5 above 2 times 2x all to the 3rd times negative y squared. I'm going to add to that 5 above 3, 2x squared, negative y to the 3rd. 2 more, stick with me, plus 5 above 4 times 2x to the 1st, negative y to the 4th, and finally 5 above 5 times negative y to the 5th. Usually at this point I step back and make sure I have the correct number of terms just to check myself before I get too far in. I have 1, 2, 3, 4, 5, 6. That makes sense. So there's my setup. I'd like you to go ahead and pause the video and try to work this out on your own. I'm not going to show you all the intermediate steps. I will say please make sure you're being careful with raising 2x to an exponent. The 2 also must be raised to that exponent. And pay attention to your negative y. When I have an even power, I should have a positive number, and if I have an odd power, I should have a negative number. All right, once simplified, I got 32x to the 5th minus 80x to the 4th y plus 80x to the 3rd y squared minus 40x squared y to the 3rd plus 10x y to the 4th minus y to the 5th. A couple things you should notice here. You should notice that your terms move back and forth with their signs because we have a alternating negative term. Your negatives flip back and forth between positive and negative when dealing with exponents. All right, the last thing we're going to talk about is an alternate method for expansion. If we don't like the binomial coefficient, we can also use Pascal's triangle. All right, so we're going to use Pascal's triangle. And the way we're going to do that is we're going to create really the same pattern we notice, where the exponents on our first term start high and descend, and the exponents on our second term start at 0 and ascend. And then we're going to multiply those together, and then multiply each term by its related row in Pascal's triangle. So for this one, we're going to end up with 10 terms. All right, we have x plus 2 to the 9th power. So I'm going to end up with 10 different terms in my expansion. So let's see what that looks like. Well, it's going to start with x to the 9th. And then there's going to be an x to the 8th term times 2. And then there's going to be an x to the 7th term times 2 squared. X to the 6th, 2 cubed. X to the 5th, 2 to the 4th. And then these problems do take up a lot of real estate, so plan ahead as you work out through your homework problems. So this will have, the next term will be x to the 4th, 2 to the 5th. There will be an x to the 3rd, 2 to the 6th, x squared, 2 to the 7th, x to the 1st times 2 to the 8th. And finally, we will have our last term will be 2 to the 9th. So we have this whole big long string of numbers. We're not quite ready to evaluate yet. We now have to include the terms from Pascal's triangle. So I need to pick the 10th row of Pascal's triangle, and I'll put these in a different color so we can see those coefficients. Well, I know that the coefficients on the first and last term will be 1, and now I'm going to work down the line. I'm going to multiply a 9 in here. That's from Pascal's triangle. My next coefficient will be a 36. Following that, I will have an 84. Following that, I will have 126 in here. And here, 126 on those two terms. And now I end up going back down and hit those same values. So I'll have an 84, a 36, a 9, and a 1. So what I can do now is evaluate each of these terms individually, and I will get to a final answer. So I'll save you the arithmetic and just write out my final answer here. I got x to the 9th plus 18, x to the 8th plus 144, x to the 7th plus 672, x to the 6th plus 2016 x to the 5th plus 4032 x to the 4th, 5376 x to the 3rd, 76 x to the 3rd plus 4608 x squared plus 2304 x plus 512. So why might we like this Pascal's triangle approach better? We might like this one better because it allows us to evaluate numbers more directly. If we're dealing with something raised to, say, the 9th power, our factorials are going to get a little bit more unwieldy and more difficult to work with. So there's two more examples here. I know this video is getting a little bit long, so I'm going to let you guys work those two problems on your own. I'm going to post these two, my final answer, and we can call it a day. For example 4, I ended up with 729 a to the 6th plus 1458 a to the 5th b squared plus 1215 a to the 4th b to the 4th plus 540 a to the 3rd b to the 6th plus 135 a squared b to the 8th plus 18a b to the 10th plus b to the 12th. One thing to be careful with here is pay attention to your exponent on the b value. So every time we raise that to a power, we must multiply that exponent times 2. And for the final problem, I ended up with 16y to the 4th minus 96y to the 3rd plus 216y squared minus 216y plus 81. Again, be careful with the negatives. You should notice that your negative sign should alternate between positive, negative, positive, negative, positive whenever your binomial is a subtraction. And that's all for today. Thank you.